Hey, greetings! Hey, there you are. I thought I lost you for a second. Greetings and welcome, friends. Today we're talking about solving systems of polar equations. And I've got a single example coming your way right here. It says find the intersections of r equals 3 minus 3 sine theta and r equals 4 minus sine theta. So I've got two polar equations. Think about these petals and circles and roses and cardioids and lemachons or whatever, right? Leprechauns. They could have all sorts of crazy intersections with one another. I think you would agree. And so I'm interested in finding out when these intersect. So I've got some r's and thetas that I want to find out. And we're going to actually solve this algebraically. And then I'll show you a graph in case you're interested, so you can see what that looks like as well. So to do this, let's solve this algebraically. Hey, you might have realized both of these are already solved for r. Yeah, they definitely are. R. So I can just like take one and plug it into the other, right? So if this is equal to r, then I could plug it into this equation's r. I think you'd agree. And so I'd have 4 minus sine theta equals 3 minus 3 sine of theta. Theta. And now I could solve for theta. And in order to do that, I'm going to want to probably group my sines together. Let's add some 3 sine theta to both sides, because those are going to be like terms, the 3 sine theta and the negative sine theta. And maybe I'll subtract the 4 from both sides while I'm at it. Why not, friends? What do you say? What do you say? So let's, 3 sine theta and negative 1 sine theta is 2 sine theta. Equals 3 minus 4 is negative 1. And let's divide both sides by 2. Right, I'm just on my way to getting theta by itself. Theta by itself. So I got sine theta is equal to negative 1/2. And now how do I... Yeah, inverse, both sides. That's how I get theta by itself, you might recall. And sine inverse will take a ratio and give me back an angle. So I'm going to get theta equals, and there's actually a couple things for us to consider first of all. Let's first figure out what is the reference angle. What is sine inverse of positive 1/2? When is sine equal to positive 1/2? No, that's root 2 over 2. 30 degrees, or pi over 6 if we're talking radians. So that's my reference angle, but now my question is, when is sine negative? Sine's negative in quadrants 3 and 4. So if my reference angle is 30 degrees, or pi over 6, I now have to figure out, so there's my reference angle, alpha. I have to figure out what's my theta going to be for this guy, right? So that's 210, and then also for this guy. And that's 330. I like that. So, so if I'm working in degrees, which... should I? All right, we'll work in degrees for the sake of... All right, you guys are lucky. So it looks like I've got 210 degrees and 330 degrees are those macro angles. Okay. So I've got two occasions when these have the same intersection, when theta is the same for both of them. So now I've got to figure out what's r when these are the same. And what I could do is then take either of, or both of these individually, I guess, and plug it into either of the original equations. Yeah, it looks like this one's a little easier. I'll plug it into this equation. So if r is equal to 4 minus sine theta, I'm just going to evaluate this twice. 4 minus sine of 210, and r equals 4 minus sine of 330. Right? And r equals 4 minus sine of 210. I already know it's negative. The reference angle is 30. In fact, I've kind of already answered this question. It's a half, negative a half, because I just kind of calculated it backwards here, and now I'm recalculating it to get the negative 1/2 there, sort of thing. Actually, I wonder, I probably could have just said negative a half is equal to sine of theta, and then plugged that into the equation for sine theta. But whatever. So I'm going to get plus a half, so r is equal to 4.5 is what I end up getting. And over here, I'd get r is equal to 4 minus what sine of 330 is. It's negative, and the reference angle is 30. Sine of 30 is a half. Same thing. Both of these actually end up equaling 4.5. So my solutions are, it's r comma theta, remember, so I want to make sure I do it in the right order. 4.5 comma 210 and 4.5 comma 330. So those are the intersections of my two graphs. So let me open up my Geometer's Sketchpad, and we're going to graph these two equations. What's up, question? Well, theoretically, they would equal exactly the same thing, yeah. Because this would have been, what, 3 plus 3 halves is what it would have been, or 3 plus 1.5, it's still 4.5, yeah. So it would work in either of them, good question. So let's take a look at Geometer's Sketchpad. So here I've got my grid, and I'm going to graph a function 3 minus 3 sine theta, and whoa, it looks like some sort of cardioid. Aw, there it is, adorable. And then 4 minus sine theta, and there we go. So it looks like it's a circle and a cardioid by the looks of things. Let me let me use this pen instead of a mouse. I'm having a hard time clicking on things. So let's increase the line thickness. And it looks like they have some intersections here. I don't know if you would agree. Let me hide these. And let's see where these intersections occur. So we actually could have had a whole bunch of crazy intersections if we'd wanted to, with different, if I had like a pedal thing going here, like it would have had intersections all over the place. But fortunately we didn't have too many. Notice, here's an intersection right there. And here's an intersection right here, and it looks like those are the only two. Where is this intersection? Well, this one's at, it looks like 210 degrees, and how far out is it? 4.5. And this one happens to be at 330 degrees, or 11 pi over 6, and that's how far out? 4.5. What do you know? So graphically, I do end up getting the same values here. So interesting stuff. You can actually find the intersections between systems of polar equations. Good stuff. So thanks for watching, friends. Have a great day. Bye-bye.